cross product. So the dot product gives us an answer that's a scalar. The cross product gives us an answer that's a vector perpendicular to the two vectors you had to start with. Perpendicular to both of them. So any two vectors, even in 3 dimensions, will be in a plane which you could then make perpendicular to both of them. So here's the cross product formula. The cross product is the length of u times the length of v times sine of theta, where theta is the angle between them, and they're joined tail to tail, times the unit vector n, and n is perpendicular to both of them. Now, if you have two vectors, you could have perpendicular coming out one direction or perpendicular coming out the other direction. Does that make sense? And so we're going to find out using what's called the right-hand rule to explain which way it goes. You will need okay, everybody has a right hand? We're good. It's all back to historical anti-left-handed people problems. Well, I will show you actually what I think is a better thing than a right-hand rule. Okay, but we'll look at it with the right-hand rule first. So here's a right-hand rule. So imagine you have two vectors, u and v, in 3 dimensions, but you could place them on that piece of paper in 3 dimensions. So if I take out a scrap piece of paper here and draw two vectors on it, right? Those two vectors could be anywhere in 3 dimensions. So any two vectors that you have in 3 dimensions, you could inevitably put on a piece of paper in 2 dimensions. And that angle of that paper would be something strange. And then your cross product will either come out 90 degrees this way or 90 degrees backwards. And that's where the right-hand rule comes into effect. So, and 2-dimensional vectors as well. And we don't go into 4-dimensional vectors. Okay, so the idea, if you wanted u cross v, you put your hand on u and you move your fingers towards v. So if I wanted to do u cross v in this situation, I put my hand on u, I take my 3 fingers, I could bend them towards v, leaving my thumb pointed up. The cross product of u dot v would come out of this paper in this direction. If I did v dot u, I cannot bend my fingers backwards. So I have to turn my hand the other way in order to bend them, and then it would go inwards. Now, I sometimes find that that description, you know, you're twisting your hand, you're like, oh, someone's always like, oh, I can bend my fingers back. You know, when they think they're bending their fingers back, they're just bending their index forward, but like, oh, look. No. And so it gets a little bit confusing. What I like to think of instead is sort of the same way when you twist a toothpaste cap on or loosen it. Same way that you would turn a bolt with a wrench. If you put your wrench on u, and cross product with v would mean turning your wrench towards v, you have to ask yourself, which way, if you turned it this way, would you loosen the cap of your toothpaste or would you tighten it? And if you loosen it, it would come up and out. So in this case, if this direction loosens it, it makes sense that it's pointing outwards. If you went v dot u and you twisted this way, that would tighten your cap or turn a screw or a bolt into, and then the direction would be the other way. They're the same thing, just different directions. So, and not dot, we say cross, because a dot was what we did previously. So this is what we just demonstrated. It's in your notes. It's explained with, I hired a very lucrative hand model for these pictures. But this other part here, which I have in the notes, I find it easier to think about taking a wrench and tightening something, or taking a toothpaste and turning it to be able to figure out which way it's going. Most people know which way to untwist a toothpaste. Well, but when I used the wrench example, it was like some people are like, I've never held a wrench or tightened a screw in my life, so I have no idea which way that is, but it's exactly the same as your toothpaste. If you've never experienced toothpaste, I would say I'd recommend, it's probably a good thing to do a couple times a day. Get less cavities. So we talked about this already. The cross product, Aidan mentioned it. The cross product, U cross V and V cross U, are not the same, but they're almost the same, just in opposite directions. So we could say that U cross V is equal to negative V cross U, because they're opposite vectors, and you can make a vector opposite just by multiplying it by a negative. So here we have two vectors, u and v. The angle between them is given to be 50 degrees. The length of u is 10. So this is 10 units long. The length of v is 20 units long. And we can find both the cross product u cross v and v cross u. Okay, so starting off, with u cross v, it's going to be the length of u times the length of v sine of theta, which in this case is 50 degrees, times the unit vector n. And when we write this, we have to describe the direction of n. So n is either going into the paper or out of the paper. In this case, we're going v cross u. So if you think about turning your toothpaste that way, would it tighten? Yes. So if it would tighten, then it's going to go into the paper. If we put our hand, right hand on this, the only way that we can move our, oh jeepers, you got to twist around and figure out which way that it's going to go. It would look like that, right? Again, I find the tightening of the toothpaste an easier analogy than twisting your hand and trying to figure out which way your thumb is pointing. So we calculate this. We go to our calculator. This is going to equal length of u was 10 times 20 times sine of 50, which I'll just write. Yes. We'll do that right at the end. So we'll get the value here. So we'll go 10 times 20 times sine of 50. Make sure that my calculator's in degrees, and it's not. 153.2. Oh, that's. Yes. So really, the length of the vector is shown by the number in front. So we have to somehow say that this one is pointing into the paper. And if it was coming towards us, we would say it's pointing out of the paper. It's not very, there should be almost a formal, feels like there should be a formal math word for towards you and away from you, but that's all we got. So this question, we were just using a formula. Oh, I didn't do the v times u. Okay, perfect. I did v times u. This is v times u, right? Because if I went v times u, that v is first to u, that's into the paper. U times v, thank you for noticing that. U times v would be going this way. It would equal the exact same thing with a negative. Either you could write this, and I would write it this way because we've already defined n to be into the paper. So by putting the negative in front, it's going to be out of the paper. Or you would have to write another statement saying that, in this case, n is pointing out of the paper. And more than once, you probably could, like it's really n is arbitrary, so you could go w and define w as a unit vector into the paper. That would be fine. Well, in this case, I put the negative out front, so that's perfectly fine. You could. Yeah. 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 Go crazy. Okay. First application of the cross product. Here's a diagram of a parallelogram. It's a little bit dark on yours, I'm sorry. In a parallelogram, the formula for the area of a parallelogram is base times height, because you could cut off this triangle, slide it over, and make a perfect rectangle. And then you would have area of that rectangle is base times height, so the area of a parallelogram is also base times height. But if I draw this diagram and I include the angle theta, I could say that sine of theta is the opposite side, which is my height, divided by my hypotenuse, which in this case is my vector v. Rearranging this, I get h by itself to be the length of vector v times sine theta. My new formula, base times height, I could now substitute my base is my length of my vector u. My height, substituting it back in, becomes v sine theta. So the number in front of your cross product without that unit vector is the area of a parallelogram. So if you just get rid of the unit vector at the end, whatever's in front of your cross product will be the area of your parallelogram. So that's shown with these absolute value bars, the magnitude of the final answer. So here was the same question that we just did, where this was 50 degrees, this length was 10, and this length was 20. We can now find the area of that parallelogram. Whatever the units are squared. Now, our formula for the cross product needed to know the angle in between them. That first formula, because it was length of u times length of v times sine of the angle. There's also the Cartesian form of the cross product, and the Cartesian form doesn't use the angle. So if you have two vectors, A1, A and B like this, we get this wonderful formula to figure out the cross product. Okay? It's actually not too bad. Okay? And it is connected to matrices and determinants. So for example, if you wanted to figure out the first one, and you covered A1 and B1, well, maybe I'll do it even here. We'll really cover it. We'll take out white, take those away. You're left with A2, B2, A3, B3. How do you find the determinant of a 2 by 2 matrix? You went like this, and you subtracted this. A2, B3 minus A3, B2. Okay? The next one, and I don't know if you remember in the 3 by 3 how it switched from positive to negative when we showed you the really long way to do a 3 by 3 inverse. The next one, if I subtract what I have here, I X out. Oh my goodness. It's not liking me right now. There we go. Now I take this one out. My determinant would be A1, B3 minus B1, A3. If I put that in brackets here and distribute the negative, that's what you have here. So whatever you can figure out the determinants of each one, and your middle one is kind of negative. Now, it's not officially called a determinant here, but we're just stealing an idea from matrices in order to make what looks like a complicated formula easy to remember and to solve for. So this is what I like to do the most. Think of determinants. Notice the last one. If I would erase this last row, here's my determinant, A1, B2 minus B1, A2. That's perfectly what's in the last one. And it's only the middle one that has the same thing but negative. There is also a form in which you can use arrows, sort of like what we did when we figured out the determinant of a 3 by 3. You rewrite ijk, ijk. You take your elements from A and write them twice. You take your elements from B and write them twice. Okay, let's do it with an actual example. So if we use this method, I have vector I, vector j, vector k, vector I, vector j, vector k. And then we take our first vector, which is 2, negative 1, 5. Write it again, 2, negative 1, 5. And take our second vector, negative 6, 3, 8, and negative 6, 3, 8. Now, we'll do it using both methods. Here's my fingers crossed that I get the same answer with both ways. Okay? Using the method we saw first, if I took out row 1, I would get negative 8 minus 15. Does that make sense? If I took out row 1 and then thought of that as a determinant, calculating the determinant of what would be left is negative 8 minus 15. And if I took out row 2 and did the determinant of that one, but put it in brackets with a negative out in front, the determinant here would be 16 minus a negative 30 plus 30 minus 46. And finally, if I did it with the third one, I would have 6 minus 6, which is 0. If you use the method where you rewrite your i's, your j's, and your k's, it's the same idea like a determinant. So, first of all, to figure out I, you need to find the vector I and go in the positive direction. You could either use, and for the positive direction I'll use green, you could either use this one, or you could do it here with this one. You get the same answer. That will give you negative 8. Good luck, guys. And then you need to take the vector I and go in the negative direction. Can you see that there's only one way that I can go in the negative direction? With I. Because this other I, there's no numbers there. That's why we write it twice. Sometimes you'll have more than one possibility. Sometimes you won't. So in this case, I have 15. So it'll be minus and then 15. For J, I go to J, I go diagonal. This is the only way I can go diagonal with J. I would get negative 30. And then I'm going to minus. And the only way I can go this way with J is 16. Minus 30, minus 16. And finally, with K, I could go two places. I could go, oh, that's not the way I want to do. Here we go. I could go only this way positive, so that will give me 6 minus, and there's two ways I could go negative. I'll take this one right here. Positive 6, 6 minus 6. No matter which method you use, you will get negative 23, negative 46, and 0. Yeah. So for this one, why is it negative? That's part of the rule for using determinants. I don't know this. Again, this is not, when I say using determinants, that is not an official method written down, but a way for you to say, an easy way for you to connect it to something else that uses the math that we've done already. Yes. Yeah. It's a great formula to use. I like the using determinants because I find it easy to visualize, okay, I'll just cover the top row and I see the next two. I cover the middle row, I can see the mathematics easy and write it down quickly. This method's great, but what's annoying about this method for me is I have to write out ijk, and all the numbers twice. Plus, I have to make sure that I space them nicely so my diagonals match up. I can't do it too quick and fast. So for ease of calculations, I like that determinant method because I can visualize it quickly and get the answer.
But it doesn't matter which way you use. The second have 0 at first, right?
The second one always, like using the arrows, will always work out that it's green minus red. It's always green minus red. And you just have to find, in order to do the second one with the j, you just have to find a j where you can write the diagonal positive. Okay, I get minus 30. J negative, okay, I get minus 60. So the nice thing about the second method is you just always green minus red, straightforward that way, not having to memorize a formula. The worst method, in my opinion, is actually memorizing the formula. Okay? That is like, okay, was it A2 or was it B3? Was it, Okay.
Is that how it's possible? Like A1, A2, A3, A4, like a 4 different vector.
No, we'll just go up to 3 by 3. Now, the nice thing about this is now we can find the cross product easily without having to know the angle. And now you could find area of parallelogram without having to know the angle. There's a lot of very nice applications of this. So here's two vectors, u and v, and the cross product of u times v. So u times v happens to equal w. Find the value of x. So here I will get you to figure out u cross v using whichever method you'd like. Calculate it and put it here. It's going to equal 2, negative 11, 19. And then we can figure out what x is. How do we do here? So did you get this one to be 3x minus 4, whichever method you used? And the next one to be negative 7x minus 3? And the last one to be 28 minus 9. Now, 28 minus 9 works out perfectly to be 19. If 3x minus 4 is equal to 2, then x would have to be 2. Double check it, though. Does it work for this one as well? If I plug in 2 here, 14 minus 3 times a negative is negative 11. That's good to double check that because otherwise you could have a problem here where x works for one part but not for the other part. Okay. Yeah. And you created your own, when dividing double u by u, since you have 2 u's divided by 1 u, the answer is 2, and it works out. Perfect. You don't like that? That's a double u. It works wonderfully. Thank you for that new insight into that question. Consider these vectors. Find the area of the parallelogram. So if we find the cross product, A cross B, we will get, and again, calculate it any way that you'd like. I'll give you a head start. Did you get -3 minus 4? 6 minus 36 and -6 minus 27 to equal -7 minus 30 minus 33. Oh yeah, positive 30. There we go. Good. And then, if that's the cross product, the length of that cross product will be -7 squared plus 30 squared plus -33 squared. Type that into your calculator. What do you get as a decimal? Does it work out nicely? Nobody's done it? All right. I am doing it right now. 45.14. Were there any units here? Find the area of the parallelogram. No. Now, find the angle between these two vectors. I do find that finding an angle between two vectors, I like to use the dot product as opposed to the cross product. The cross product will give you the angle as well. The problem with the cross product is you can't determine whether the angle was acute or obtuse, because sine of theta could be possible in quadrant 1 or quadrant 2 according to your cast rule. So using the cross product using the dot product, that cos of an angle theta is u dot, is that the letters we have here? We have A and B. A dot B over the length of A times the length of B. Okay? So the dot product for these two, I should just rewrite them here so I can see them. -6, 3, 4, and 9, 1, -1. So our dot product, -54 plus 3 minus 4. The length of A, 36 plus 9, 45 plus 16, 61. The length of B, 81 plus 1 plus 1, 83. So now we can tell that, yes, the angle is obtuse. Because if we do our math on the top, we're going to get -55 over the square root of 61 times 83. And cos inverse of, now if you do cos inverse of the positive angle, you will get the reference angle and then have to figure it out in quadrant 2. If you do cos inverse of a negative angle, it will give you the angle in quadrant 2. 61 times 83. 140.6 degrees. So had we used the cross product formula, you probably would have got 39.4 degrees and not been able to tell, oh, should I use that or should I use, well, first of all, you'd probably just go, ooh, I got an angle, and stop. That's the typical student response when they get an answer. I got an answer, I'm going to stop. So this is why using the dot product to find an angle is better. Properties of our cross product? Well, we already know that the order matters, but it's just the opposite direction from one to the other. You can distribute the cross product. I have no idea why you would want to. Okay? Because we know that adding two vectors is really easy to do. You just have to add components. Cross product, even if you use what I think is the easiest method, which is that determinant method, there's still a lot of multiplying and things, and then you would have to do that twice before you added them up. So yes, you can distribute it. Recommendation, no. Okay? If the cross product is 0, that means that your original vectors are parallel. So you have a problem. If you have two parallel vectors tail to tail, there's like an infinite amount of perpendicular ones that go around, so that makes our cross product equal to 0. And similarly, this is important in higher level mathematics. Just because one thing is true does not necessarily imply that the other statement is true. Right? All horses have 4 legs. Does not imply that all things with 4 legs are horses. Right? Because you can't always go in both directions. Well, yes. Okay? You're essentially, as soon as you do it with a 2-dimension, you pull it into a 3rd dimension. So a 2-dimensional vector is just a 3-dimensional vector with zeros for z. So our cross product is really meant for the real world and real world applications.
So reasonably speaking,
You could. You could make.
6 dimensions just by adding zeros.
You could. Yes.
And then doing it, like if we could do the cross product.
And if you have a scalar product, you can put that scalar with any part. Usually I would, again, recommend just doing it at the end because that makes your mathematics easier as you go. At the end, Eric, make sure that what you missed on this question, I can put it up at the end to mark it down. Okay? So, example 6. Here we have 2 vectors. Show that these vectors are parallel. So, using the properties, A cross B should be the 0 vector. Okay, so here I would get -4 minus a -4. Second one I would get 6 minus 6. And the last one I would get 12 minus 12, which yes, parallel. This is a fancy L. Parallel twice. Wow. Parallel. Okay. Another application. The physics formula for torque. And this is where that whole idea of me putting a wrench and turning it in one direction or another, fascinating. That's still, it's all built in with the cross product. And it's fascinating. Fascinating. Okay. Torque is the measure of force on an object which causes it to turn. Here's the formula for torque, is just the cross product of the length of your object, the arm that you have, and the force that you give. And the units are Newton meters. Consider a wrench 15 centimeters long. Right. So since the units are Newton meters and we have 15 centimeters, we can change, here's the wrench, 0.15 meters. We can think of that as one of our vectors. Now, we are applying a force of 50 newtons to the wrench at an angle of 85 degrees, and we're doing it in the clockwise direction. So we can imagine first this vector getting pressed on here with 85 newtons. No, 50 newtons, sorry, the 85 is the angle, at an angle of 85 degrees. Now, in order to do the cross product, your vectors have to be tail to tail. So we would need to take this vector and redraw it tail to tail here with 50 newtons. If these are parallel, which they are, does it make sense that this 85 transfers? The green ones are parallel. Yes. If the green ones are parallel, then the angle of 85 there would translate to same as the angle of 85 there. Okay. So then our torque, which is our fancy, oh, I'm not very good at drawing that, that torque symbol. Right now, draw tau. The length of A is 0.15. The length of the green one is 50. Hence the units of Newton meters, because you're multiplying your newtons by your meters. And we have sine of the angle of 85. .15 times 50 times sine of 85. Now, if you just type in 7.47 Newton meters. If you just, yes. Fair enough. I like it. Feels like it needs a dot, but yeah. But it's fine. So, if you think of it, what angle gives you the biggest value for sine? 90. Okay? And whenever you're pressing on a wrench, it makes the most sense to press at a 90 degrees because you'll get the most torque. If you press at a 0 degrees, that means you put your wrench on there and like, right? That is not very efficient at all. Right? Now, in this case, it's going in a clockwise direction, like this. Think about your toothpaste. Will we be tightening or will we be loosening? A standard if we think of this, no, it is a toothpaste thing. They don't come any other way. There you go. You should. There is reverse threading, but I don't think it exists on toothpaste. Not yet.
I buy left-handed toothpaste.
So in this case, it should tighten. This is a bolt. And it does say tighten, so it makes sense that this is a regular.
It says clockwise and tighten. We can't assume it unless it says both, which means that it's tightening in the clockwise direction.
Which is a normal threaded, which is what kind of thread, if it's normally threaded? Righty-tighty, lefty-loosey. I learned that too. Oh my goodness. So the magnitude was 7.47. Did I write it down right? Yes. And direction into the paper. And then we already answered what angle should the force be applied to maximize 90 degrees. So we're going to take the rest of class to work on these. Eric, what your notes that you missed, I'll put them up. Did you get